Last time in our lecture 17 in our series in numerical methods in civil engineering, we talked about conjugate directions in general. This time we will complete our discussion of conjugate directions, right. We just started with that. Basically we will complete that, and then we are going to talk about the method of conjugate gradients. We looked at one gradient based method already, and the method we looked at in detail was the method of steepest descent, where we go along a particular direction, we try to minimize the function in that direction, and then we move along in another direction. There is no guarantee that the direction in which we are moving, we are not going to retrace our steps, right, because we often come back and take the same steps in the same direction, the steepest descent method, because there is no requirement requiring those steps to satisfy any relation with respect to each other. The directions in which we travel, the directions in which we move, the steepest descent directions, basically the gradient, the negative of the gradient direction, it does not, there is no restriction or there is no requirement that those directions satisfy any relationship between each other, right. Because of that, we can move in the same direction several times during the course of our iteration. But this is not very economical, or this is not very efficient, because we are having to retrace our steps. Ideally, what we should do is that we should go in one direction, exhaust all our possibilities in that direction. By exhaust all our possibilities, I mean that we minimize the function in that direction. If there is an error, if there is a global component of error, if we think of a global error vector, so in that direction we make the component of the error vector fully 0, right, and then we move on to another direction. But when we move to the other direction and we try to minimize the function in that direction, we do not want errors to be creeping back in a previous direction that we have traveled, right. We want those errors to be, the directions to be orthogonal, number 1, and number 2, we want to make sure that the errors do not grow again in that direction, right. So, both those requirements are fulfilled by some of the methods that we are going to talk about today, right. This can be done if we make sure that the search directions are orthogonal to each other, and in each search direction we take steps of exactly the right length. That is going to, of course, minimize the function in that direction. And then in an n dimensional space, after n such orthogonal steps of exactly the right length, we are sure to reach the minimum, provided we do not, the error does not grow back in that direction, right. That is a very important criteria. The idea is that ideally during a particular step in the iteration, we exhaust the error in that direction, and we ensure that the following step introduces no additional errors in the direction of the previous step. That is, the update ensures that if xi plus 1 is equal to xi plus alpha I di is my update law, with alpha I such that xi plus 1 minus x dot di is equal to I plus 1 dot di is equal to 0. So, basically I am saying that the error at the I plus 1th iteration, the error vector at the I plus 1th iteration, which is this quantity, right, xi plus 1 minus x, this does not have any component in the di direction, right. This error vector in the next iteration, it has got no component in the di in the previous direction, right. The error vector at iteration I plus 1 can be written in terms of the previous step directions dk. How can we do that? Well, let us see what we can do. We know that error at I plus 1, ei plus 1 is equal to xi plus 1 minus x, right, that is by definition, and this xi plus 1 by our update rule is equal to xi plus alpha I di plus minus x, right. So, xi minus x, if I pull it together, that becomes ei, the error at iteration I, plus alpha I di. So, then if I write ei in terms of ei minus 1, the error at the I minus 1th iteration, and d minus 1, the direction at the I minus 1th iteration, then we can do this recursively. Eventually, we will end up with the equation for ei or ei plus 1 in terms of my original error vector E0 and all my directions that I have travelled up to that iteration, up to the I plus 1th iteration. So, eventually we are going to get something like E0 plus sigma k equal to 0 to I alpha k dk, because all these di's are going to have components, right. So, the error at I plus 1 is equal to my original error plus sigma k equal to 0 I alpha k dk. This equation, it is very it has a lot of meaning, right. What it is saying is that, you think about it, it's saying that the error at some iteration at the end I plus 1 is equal to my original error plus this alpha k dk. So, what these alpha k dk are doing is actually they are eating away the error. So, E0 is my original error. So, every time I take this dk, this E0 something is changing in that E0, right. So, eventually when I take n iterations, all that error in E0 has been nullified and En plus 1 is eventually equal to 0, right. So, at the end I get 0, right. So, let us go back to that equation. This equation, right, equation gives me an expression for alpha I. How does it do that? Well, what it says is that di dotted with ei plus 1 equal to 0. So, I can write that as di dot di transpose ei plus 1 equal to 0. So, di transpose ei plus alpha I di equal to 0 from my equation right here, right, from my equation right here, ei plus 1 equal to ei plus alpha I di. So, ei plus alpha I di equal to 0. So, that gives me an expression for alpha I. But what do you see about this expression? This expression has alpha I on the left hand side, and on the right hand side it has di as well as ei, right. This is not useful at all. Why is it not useful? Because I want to know what step I have to take in the alpha I direction, right. At that point I have no idea what will be the result of my step, right. So, I have no idea what the error will be. So, I have no idea what ei will be, right. So, after I take the step alpha I, then I update my variable x I plus 1, only then can I calculate the error, right. But it is saying that in order to know how much to travel in that direction, I have to know what the error will be, which is impossible, right. So, this is a theoretical, this is a good, it is a nice equation, but it is practically useless, right. We cannot use it to calculate our step length, right. So, how do we calculate our step length? So, in order to calculate our step length, we must be using information which we already know, right. For instance, we know the residual at step I, that we can use, or we know the residual in the previous steps, that we can use. I know the directions in the previous steps, that I can use, and things like that, right. So, I should not be using information which I do not know yet, right. That does not make any sense. But in order to, so how do we get an expression for alpha I which we can actually calculate? Well, in order to do that, we impose a certain a new notion, we actually introduce a new notion of orthogonality, right. We say that we are not going to make the error ei directly orthogonal, ei plus 1 directly orthogonal to di. We are not going to impose that restriction. We are going to impose this restriction, ei is orthogonal, ei plus 1 is orthogonal to di with respect to this matrix A, right. So, this is like some sort of a normally when you think of an inner product, right, you just think of an inner product as the dot product of two vectors, right. That is true in a Cartesian space, right, but in a space where there is a different metric. I do not know if you are familiar with the notion of metric. In the Cartesian space, the metric is the identity tensor, it is the identity matrix, right. That is why we can calculate dot product as ei transpose di, right. It is basically we are actually doing ei plus 1 transpose identity di, right, because identity is the metric in that space, in the 3-dimensional Euclidean space, in the Cartesian coordinate system. But there are some systems where the metric is not the identity tensor, right, it is not the identity matrix, right. So, in those for instance, when you are thinking of I can think of structural mechanics applications, right, when one thinks of shell structures and things like that, curvilinear coordinate systems, right. In that case, the notion of length, because the inner product, the dot product is intimately related to the idea of length, right. If you have dot product, if you take dot product of a vector with itself, that is the square of the length of the vector, right. So, the dot product is very related to the idea of norm, of length, right. So, I do not want to digress too much, but I am saying that this is a very common idea in, well, in lots of fields. Basically it started with differential geometry, but there are lots of fields where this idea is used, right. The idea of a metric, of a tensor which actually defines, or a metric, or a matrix which actually defines a dot product, which defines a length, right. So, in this case we are saying that here our a matrix which defines a dot product is this A matrix. So, any dot products we calculate are going to be with respect to the A matrix. So, it will be of this form, right. And when we say that, normally when we say that two vectors are in my usual Cartesian space, right, if I say that everything is planar, I say dot product is two vectors are orthogonal if their dot product is equal to 0. So, now the idea of orthogonality has changed. So, dot product means that those two vectors are, their dot product is equal to 0, but the dot product is defined with respect to a particular matrix, right, which is my metric, right. So, instead of making the search directions orthogonal, we make them A-orthogonal, right. So, this A-orthogonal, orthogonality with respect to this metric A. That is, we now require di transpose A di minus 1 is equal to 0. So, all the previous directions are orthogonal to my current direction, but with respect to A, right. So, progress can be made in obtaining, if we do that, we can get a practical expression for alpha. Okay. So, from star we get, so now instead of this, basically we will go back to this equation, right, and now we will say ei plus 1 dot A, ei plus 1 A dotted with d1, right, equal to 0, right. So, if we do that, then we get an expression for alpha I, which is minus di transpose AEI di transpose A di. So, compare this expression with my earlier expression. The only thing that has come is that A, right, and this changes the whole thing, because I know that AEI is RI, right, because AEI is equal to A xi minus AX, where x is my true solution, right, and I know AX is equal to B. So, this is AXI minus B, which is nothing but my residual, right. So, I already know that, right, I know already the residual at I, right. So, I can use that here. So, I have di transpose Ri di transpose A di. So, now I know everything, right. I know the direction that I have to travel, of course, I know the direction that I have to travel. I know the residual, the error at the ith iteration, I mean not, it is the residual at the ith iteration, and then if I use these two things, I can calculate my step alpha I, and then can move in the di direction by that step. Since the right hand side comprises known quantities at step I, this allows for ready evaluation of alpha I, right. In case di is equal to Ri, I do not have the steepest descent formula with me, but if you look, if you go back to last time's lecture, you will find that for the steepest descent method, only thing that is different was that di is instead of di we have Ri, right. We recovered the formula as in steepest descent. So, it can be shown that enforcing the above orthogonality condition ei plus 1 transpose A di is equivalent to requiring that the error be minimized along the search direction di as in the steepest descent method. So, when we impose this condition, we are all actually enforcing the condition that the error is actually minimized along the direction di, right. We saw that for steepest descent. It turns out that is true for the method of conjugate directions as well. So, minimizing the error in the search direction is equivalent to minimizing the function in the search direction, right. So, basically want to minimize the function in order to minimize the error, because what we are interested in doing is finding the minimum of the function. So, if we minimize the function in that direction, we are also minimizing the error in that direction, right, because our purpose is to minimize the function f, right. So, we want to minimize that function in the di direction. So, how do we do that? We take the directional derivative, right, dd alpha of f x I plus alpha I di equal to 0. So, this if we evaluate, this is nothing but the gradient at x I plus 1 transpose di, right. This is actually x I plus 1, right. So, gradient at x I plus 1 transpose times di, that must be equal to 0, right. So, this I showed you how it comes, right. We are first taking the gradient of f with respect, derivative of f with respect to its argument, and then taking the derivative of the argument with respect to alpha, right, alpha I, and that is how we get this di, right. So, that is the condition I get. But let us see, and let us take a look of for the equation for a quadratic form, which is f x is equal to f p plus p minus x transpose a p minus x, right. Therefore, gradient of f x is equal to a p minus x, a p minus a x is equal to b. So, a p minus b equal to minus r, right. So, basically what this condition, what it is saying is that the residual, this is nothing but the residual, a gradient of f at x I plus 1 is equal to the residual at I plus 1. The residual at I plus 1, it is actually the negative of the residual at I plus 1, that is orthogonal to di, right, that is orthogonal to di, which basically means that di dotted with a e I plus 1 equal to 0, because r I plus 1 is equal to a e I plus 1, right, a e I plus 1. So, what do we see from this? What does this tell us? This tells us that if we are minimizing the function in this direction, in the di direction, what we are actually doing is we are satisfying this condition. We are satisfying the condition that di is orthogonal to e I plus 1 with respect to the A matrix, right, with respect to the A matrix. So, di transpose A e I plus 1 equal to 0. Is that clear? Thus, we see that the orthogonality between the error and the previous search direction follows naturally from minimization of the error in the search direction. So, we minimize the error in the search direction, this automatically leads to the orthogonality of the search direction with the error. We saw earlier that the error in the I plus 1th step can be expressed in terms of the error in the 0th step and a linear combination of the search directions. We saw that earlier, right, that error at any I plus 1 is equal to my initial error E0 plus some linear combination of my search directions, right. We saw that already. So, does orthogonality of the search directions truly ensure that n dimensional quadratic is minimized after n steps, that is n e n equal to 0. So, what we have seen up till now? We have seen that if we minimize a function along its if we minimize that function along at a particular direction, we get orthogonality between the error and the previous search direction. That is all we have seen. But does that really lead to the minimization of the function in n iterations? That is what we want to see, right. So, if the function is truly minimized after n steps, it would mean that E n, the error at the end of n iterations, is equal to 0. So, how do we, so to show this, we express the initial error E0 as a linear combination of my search directions. Why can I do that? Why can I do that? Why can I show that I can express my initial error is this? I know this I have shown already, right? EI plus 1 is equal to E0 plus sigma k equal to this I have shown. But now I am saying that my initial error I can express it as a linear combination of my n search directions. Why is that? Well, that is simply because my n search directions are mutually orthogonal, and since they are mutually orthogonal, they form a basis in my n dimensional space, right. So, any vector I can express as a linear combination of my search directions, right. So, I am expressing the vector E0 as a linear combination of the search directions, and then I pre-multiply this expression by dk transpose A, right. So, I get dk transpose A E0 delta j dk transpose A dj. You have a summation here, right, but basically recall that all my search directions are mutually orthogonal to each other, not just orthogonal, but a-orthogonal to each other, right. So, all these terms dk transpose A dj are going to give me 0 unless the two indices k and j are identical, right. When that happens, then I get this term delta k dk transpose A dk, right. So, that is true since dk transpose sigma j equal to k minus 1 alpha j dj equal to 0, which is basically because they are orthogonal, right, they are orthogonal. So, what do we have? So, we can write delta k, these coefficients, we can write these coefficients as the quotient of dk transpose A E0 and dk transpose A dk, right. So, I can write that. So, then I take out, then I look at the numerator, I have dk transpose A, and then I do a little trick. I say instead of I have E0 here, I write E0 plus sigma j equal to 0 up to k sum over j equal to 0 to k minus 1 alpha j dj. Why can I do that? Because I know that this term with if I take the dot product with dk transpose A, that is going to give me 0, because all these directions are A orthogonal to dk, right. So, I can write it like this divided by dk transpose dk, but again then we have already seen that this expression is nothing but ek, right. So, what we are saying is that delta k is equal to dk transpose A ek divided by dk transpose A dk, right. So, compare this expression for delta k. Recall what is delta k? Delta k is nothing but the coefficients of the dk's of the dj's in my original error vector, right. So, E0 is equal to sigma j equal to 0 to n minus 1 delta j dj. So, delta j I found is this, or delta k is this, right. How does this compare with my expression for my alpha k's, which I obtained earlier? Look at this. This is my expression for the alpha k's, right. Di transpose AEI, di transpose ADI, and this is di transpose AEI, di transpose ADI, but that one had a negative sign. So, basically I found that my alpha k and dk are equal in magnitude, but they differ in sign, So, this is very revealing, because this leads to a new interpretation of the error, because what are the alpha k's doing? The alpha k's are updating my iterates, right. xk plus 1 is equal to xk plus alpha k dk. And what is my delta k doing? Delta k is a coefficient in the expansion of the original error. So, what it is saying is that every time I take a step, I change my trial solution by alpha k in the direction dk, but simultaneously I am going to change my because alpha k is equal to delta k. So, I am changing my error also by the same coefficient, right. My error is reducing by the same amount, right, because alpha k is equal to delta k. So, building up, I should not say the error is reducing, it is a little vague statement, but the same coefficient, right, the same coefficient in the error expression, right. So, building up the solution step by step as in x I plus 1 equal to x I plus alpha I d I is equivalent to reducing the error component by component, right. So, this is evident from let us see it in a little more detail. So, we know this expression x I is equal to x I minus 1 plus alpha I minus 1 d I minus 1, that is always true, right. That is just my update rule. And then if I subtract my true solution x from both sides of this equation, on the left hand side I have E I, on the right hand side I have x I minus 1 minus x, which is E I minus 1 plus alpha I minus 1 d I minus 1. But this I can write, then again I can expand E I minus 1 in the similar way, right. Again I can write E I minus 1 in terms of d I minus 2, right, and stuff. So, eventually I am going to end up with E 0 plus sigma j equal to 0 to I minus 1 alpha j d j, right, just by recursion, right, continuing this step. So, I know E I equal to E I minus 1 plus alpha minus 1 d I minus 1, right. So, here I am going to put E I minus 1 is equal to E I minus 2 plus alpha I minus 2 d I minus 2. Then again I am going to replace E I minus 2 similarly, right, just continue, just do recursion, right. So, eventually I am going to get E 0 plus this term, right. So, this then again E 0, I assume that I could write E 0, I know that I can write, I did not assume that, I know I can write E 0 in terms of delta j d j, right, then n directions because they are orthogonal, they form a basis. So, then let me replace that expression for E 0 here. So, E 0 is equal to sigma j equal to 1 n minus 1 delta j d j, and now I will replace alpha j by minus delta j, because I already found that alpha I is equal to minus delta I. So, I replace alpha j by minus delta j. So, now what do I have? I have j equal to 0 to n minus 1 delta j d j, which is my initial error, minus this term, minus this term. So, I am left with the summation only from j equal to 1 to n minus 1 delta j d j. So, this is very revealing, because what it says is that initially my error had components from in all the d directions, from j equal to 0 to n minus 1, d 0, d 1, d 2, dn minus 1, right. Now after I steps, after I minus 1 steps, my error has components only in the directions d I to d I minus 1. So, from 0 to I minus 1, all those components of E 0 have gone totally to 0, right, they have been totally negated, because now I can write the error at step I in terms of the basis vectors I j equal to I to n minus 1. So, it no longer has components in the basis vectors 0 to I minus 1, but remember my original E 0 had components in all these directions, right, from 0, 1, 2, 3 up to n minus 1. So, the components in the directions 0 to I minus 1 have gone away, right, because of my iteration, right. So, this is the proof that if I do n iterations, my whole error is going to go away, because all my components are going to go to 0. Every time I take a step, one component is going away, right. So, eventually when I take n steps, all my components are gone, right. So, this is a proof that this conjugate method of conjugate directions is actually going to converge in n iterations, right. So, after n iterations, therefore, every component of the error will be annihilated, that is En equal to 0. Thus, the A orthogonality of the search directions does indeed ensure that n dimensional quadratic form is minimized after n steps. For after all, this is the only condition that we have used, right, that the search directions are A orthogonal to each other. A orthogonality of the search directions ensures that n dimensional quadratic form is minimized after n steps. The question which we have not answered till now is that what are my directions, right. I say that there are n directions, they form an orthogonal, right, they are orthogonal, they form a basis in that space, right, and they are also A orthogonal to each other, right. So, but then how do I find those search directions, right? Well, I find those search directions by a method which is known as Gram-Schmidt orthogonalization. It's a very common method in numerical analysis and thing which we have already encountered earlier in this course. So, we use the conjugate Gram-Schmidt process. So, what does it say? Well, it says that if I start with any n linearly independent vectors, note that these vectors need not be orthogonal, they need only be linearly independent, right. Then linearly independent, to construct di, to construct any search direction di, we take ui and project out the components of ui in the previous search directions. That is going to result in ui, after I remove all those components, whatever is left in ui is going to be orthogonal to all my previous search directions, and that transformed ui will become my new search direction, right. So, construct di, we take ui, project out the components of ui that are not orthogonal to the previous d vectors, right, those which have components along those along the previous d vectors I remove, and the previous d vectors meaning the vectors d0, d1, d2 to di minus 1, right, and whatever is left is assured to be orthogonal to all these vectors d0, d1, d2, di minus 1. So, what is the algorithm? Well, we start with d0 equal to u0, because when we have d0 there are no such directions, that is I am just starting my algorithm, right. So, I just set u0 equal to d0, and then when I move to the next one, next iteration, when I want to compute my next search direction, I make sure that I subtract, I start with u1 then, and I take away from u1 the projection of d0 in the u1 direction, right. So, di is equal to ui minus sigma k equal to 0 I minus 1 beta I k dk, where beta I k are the projections of the ui in the search directions dk. So, dk k equal to 0 to I minus 1, which is very important to note, right. I am taking the projection with respect to the previous search directions, right, up to I minus 1 I am taking the projection. To find beta I k, we use the A orthogonality of the d vectors. So, take the dot product of star this expression in the direction dj again with the metric A, right. So, we are going to enforce A orthogonality, right. So, I take di transpose A dj. So, that gives ui transpose A dj minus sigma k equal to 0 I minus 1 beta I k dk transpose A dj, right. So, this part remains the same, but this part I use the A orthogonality of the direction vectors, and I end up only with dj transpose A dj for I greater than j, right, because the summation here is from k equal to I minus 1, right. So, all these terms are going to go to 0 for I greater than j, right. For I greater than j, since they do not contain, they are all less than I minus 1 up to less than I. So, all those terms are going to go away. The only term that is going to survive is dj transpose A dj, right. So this gives me that. So this allows me to calculate beta ij from this expression, right. From this expression I get beta ij equal to minus ui transpose A dj divided by dj transpose A dj. What does it mean? It means that to compute each of these beta ij's, I have to know all my previous search directions, right. Suppose I am computing my third search direction, right. I am computing my third search direction. So, I know D0, I know D1, I want to compute D2, right. I want to compute D2. So, let us look at this equation again. So, I will compute D2, but then I have to take this sum from k equal to 0 to 1, right. So, here what do I have? I have beta 2 1 d1 plus minus beta 2 2 d2, right. So, not only but this beta 2 1 and beta 2 2, they involve my vectors d1. They would sorry, we want to calculate not only beta 2 1, we also need to calculate beta 2 0, right. So, they involve they involve my vectors 1 and 0, right, because this is j, right. So, they involve the vectors d0 as well as d1. So, at any point, suppose after 10,000, if I have a huge problem, right, and my matrix is of size 20,000 by 20,000, after 10,000 steps, how many directions do I have? I have 10,000 directions, right. So, I have to keep all those 10,000 directions to evaluate my new direction. To evaluate my 10,001th direction, I have to keep all those directions, and then I have to perform this operation, right. I have to perform this operation to calculate my coefficients and then use my equation here, right. So, that is not a good idea. I mean, it can be done, but it is not feasible. In any real problem, with a large problem, if you have to store all those vectors and at each step you have to do all those multiplications and all those divisions, that is going to be awfully expensive, right. So, that is a big disadvantage of the method of conjugate directions. That is a disadvantage of the method of conjugate directions, and when we go to the method of conjugate gradients, we will see that the beauty of the method of conjugate gradients is that it overcomes this problem. It gets around this problem, right. So, it gets around the problem of storing all the previous search directions and having to compute all these coefficients every time we do a Gram-Schmidt orthogonalization to find the new search direction, right. So, we have already talked about that. Computing beta ij is computationally expensive. Because of this, the method of conjugate directions was not widely used till a modification to the original algorithm, the method of conjugate gradients, was discovered, right. So, until we discovered the method of conjugate gradients sometime in the early part or the middle part of the last century, this method of conjugate directions was known for a long time, but people did not use it because of this drawback, right. So, we will talk about the method of conjugate gradients, which allows us to circumvent this problem, but before doing that, I want to talk about another important property of the method of conjugate gradients, method of conjugate directions, which is that it finds the best solution within the bounds of the space where it has been allowed to operate. What do we mean by that? Well, let us see. Well, we know that at any iteration I, ei is equal to E0 plus k sigma k equal to 0 I minus 1 alpha k dk. We have already seen that, how we got that, right. Now, let us suppose di be the I dimensional subspace spanned by my directions d0 to di minus 1. So, I am looking at step I now. I have already travelled in the direction 0, 1, 2 up to I minus 1, and I am denoting that subspace that and I know that all these vectors they form a basis, right. So, the subspace that is spanned by these basis vectors, right, I am going to denote by di, right. And what my equation here tells me is that the error at step I is a combination, can be written as a combination of my basis vectors d0 to di minus 1, basically my subspace di, and my original error vector E0, right. Shows that EI is chosen from E0 plus di. Now, the algorithm chooses the value from E0 plus di that minimizes the norm of the error EI in the, when I say norm, I define norm with respect to the A metric, right. So, we can show that. Well, how can we show that? Well, since EI is equal to sigma j equal to I to delta j dj, right, I can always write that because my dj, my basis dj, they form a j equal to I to n minus 1, they form a basis, right, and we have already shown that, right. That is not really, we showed that sometime exactly here, right. We showed that exactly here because the errors are all the I minus 1 components have been annihilated, right. So, because of that I can write this dj j equal to I to n minus 1 form a basis for my EI, right. I can write the EI as a linear combination of those limited set of dj's, right. That limited set of, this is the very important, that limited set of dj's, right. So, every time the basis, it is a very beautiful thing, right. Every time I am taking an iteration, I had originally my basis was n dimensional. So, every time I am taking an iteration, my basis is changing. So, basis is again reduced by 1. So, my space, the space that is spanned by the basis vectors is also getting reduced by 1. So, you think of it in simply in 3D, I start with a 3 dimensional vector, it becomes a 2 dimensional vector, first iteration, next iteration it becomes a scalar, and then I am done, right. So, basically we can write EI equal to sigma j equal to I to n minus 1 delta j dj from which we have already seen. Then if I calculate the norm of this error in with respect to the A matrix. So, basically I evaluate this modified inner product, which is my new definition of a dot product, right, EI transpose AEI. So, I take the dot product of this with itself. So, I have delta j delta k dj transpose A dk, right. Again I am going to use the A orthogonality of the direction vectors, and I am going to end up with sigma j equal to I to n minus 1 delta j square dj transpose A dj, right. So, now what does it tell me? Each term is associated, each term in this expression is associated with a search direction that has not yet been travelled, right. So, all the remaining error after I iterations is associated with a search direction which is not been travelled, right, because what is the j index varying from? It is varying from I to n minus 1, right. Each term is associated with a search direction that has not yet been traversed. If di be the I dimensional, this I have already talked about, right. So, any other vector E chosen from E0 plus di will include components along the previously traversed search directions, and thus will have a larger energy norm. Why? EI is chosen from E0 plus di, right. Di has all these components d0, d1, di minus 1, right. But eventually we see that EI has got components, it does not have any components in d0, d1, di minus 1, right. It has got only components in the basis from I to n minus 1, right. But if I consider any other vector E which is chosen from E0 plus di, it will include components along the previously traversed search directions, right, because this di consists of d0, d1 up to di minus 1. So, if I choose any vector, any arbitrary vector from that search direction, from that space, that subspace which is basically di plus E0, that may have, that is going to have a component along the previous directions, right. But my EI, which also belongs to that exact same subspace which I just showed earlier, right. EI is chosen from E0 plus di. EI however has got no components along the previous, along di, right, along in the subspace di, right. So, that means that EI is the minimum, right, because it does not have any components along the di's, right. Any other vector from that subspace is going to have components along those directions, right. So, any other vector E chosen from E0 plus di will include components along the previously traversed search directions, and thus it will have a larger norm. Why will it have a larger norm? Because it will include not only this j equal to I to n minus 1, it will also include terms involving I minus 1, I minus 2 and so on and so forth, right. So, this does not include any components of in the subspace spanned by di, right. So, this basically shows us, what does it show us? What we intended to show was that, not that, let us see, no, where did we state that? No. So, that the method of conjugate directions finds the best solution within the bounds of the space where it has been allowed to operate, right. Because it finds the best solution because it gives me the minimum error. So, up till now I have allowed it to operate in the space di, right. I have allowed it to operate in the space d0 E0 which I started with, and di, right. So, in that subspace it gave me the best solution, right. So, that is the idea. So, let us talk about another important property of the method of conjugate directions, which is that the residual at step I, the Ri, is orthogonal, not A-orthogonal in this case. It is orthogonal to the old search directions, that is Ri is orthogonal to the space spanned by d0, d1, d2 to di minus 1, which I called di, right, which is basically the same thing as di. So, the residual at iteration I is orthogonal to the space spanned by these vectors. Well, how can we show it? Well, look at this. Recall we have EI equal to sigma j equal to 1 to n minus 1 delta j dj, that is EI has components only in the vectors stretching, it does not have any components from 0 to I minus 1, which implies if I take dk transpose AEI, I get delta j dk transpose A dj, and this is going to be 0 for all k less than I, right. For all k less than I, this is going to be 0. But since A minus AEI is equal to Ri, we get from the A orthogonality of the search directions dk transpose Ri is equal to 0, right, because this AEI is nothing but Ri, right. So, I get minus dk transpose Ri is equal to 0 for all k less than I. So, at residual I, at I, the residual R I is orthogonal to all the k's for which k is less than I. That means, that is orthogonal to all the previous such directions, right. So, the residual is orthogonal to all the previous such directions. Then, since the search directions are constructed from the set of linearly independent vectors u0 through ui minus 1, this means that the search directions d0, di, di minus 1 form an orthogonal basis for this subspace. Thus, the subspace spanned by u0, ui, u minus 1 is di. So, basically I am saying that I got my d0 through di minus 1 from my I minus 1 linearly independent vectors u0, ui to ui minus 1, right. But I know that my d0, d1, di minus 1 forms an orthogonal basis, right. Forms an orthogonal basis. So, this is an orthogonal basis for the space u0, ui minus 1, and therefore, the subspace spanned by u0, ui minus 1 is actually also di. Is that clear? I do not know if it is clear. It's what I am saying is that my di's I formed from my u0, ui minus 1 vectors, right. So, the subspace spanned by those mutually independent I vectors u0, u1 to ui minus 1 must be identical to the subspace that is spanned by my d vectors, right, d0, d1, di minus 1, right. So, those two subspaces must be orthogonal, and since R I is orthogonal to the d0, di vectors, right. So, that means what? R I is orthogonal to that subspace spanned by those vectors, right. R I is orthogonal to any vector which can be formed by a linear combination of those d0, di minus 1 vectors. That means that R I must be orthogonal to also my u vectors, right. It must be orthogonal to my u vectors, because I can always write those u vectors as a combination of those d0, d1 to di minus 1 vectors, right. So, R I is orthogonal to those u vectors. Well, we can show that. So, 0 is equal to di transpose R j, which we have already shown, right, that the residual R j must be orthogonal to all the previous di's, right, for I less than j. So, then we write di in terms of this expression, right. How did we get that expression? Well, this is how I calculated my di from Gram-Schmidt orthogonalization, right. So, I replace that di by this expression, I get ui transpose R j, ui transpose R j plus this term which is k equal to 0 to I minus 1 beta I k dk transpose R j, but this is going to be 0 because k goes from 0 to I minus 1 and j I know is greater than I. So, this has got to be 0. So, this term has goes to 0. So, I have ui transpose R j. So, from this I get di transpose R I is equal to ui. So, di transpose R j is equal to ui transpose R j. So, it also means that di transpose R I is equal to ui transpose R I, right, in case, right. And this property is used in the formulation of the method of conjugate gradients. So, now we are ready to talk about the method of conjugate gradients, and we will see that the method of conjugate gradients is nothing but the method of conjugate directions, but with one very important difference, and that important difference gives the method of conjugate gradients all its power. It results in my not having to store all my previous direction vectors when I compute my new direction vectors. It leads to huge savings, right, and it allows the method of conjugate gradients to be used to solve very large problems which cannot be solved by normal direct solver, right. If I have a 1 million by 1 million system, I probably, even if I use Gauss elimination, if I use all the efficiencies I can muster, I probably will have a hard time solving it, right, in most computers. But the method of conjugate gradients can be used to solve that system, and that is precisely because that it has overcome the debility with the method of conjugate directions, right. Thank you.